Thank you. It's really a delight to be here. I love coming to Montreal, and I can now say that I was here in the snow, although I was told that that was like a big exaggeration for what the weather actually was today. But in Vancouver, it will be worth some points. So I had to think a little bit about what I should talk about tonight. It was wonderful, really exciting to get this invitation from an organization that is, works around music and sound, because I work with the sense of touch, but and of course there's connections between these, but they're very different mediums. And so I asked what I should talk about, and they said just talk about what you do. So I'm going to talk about one of the things I do, and leave it to you to find the commonalities that are interesting to you here. So it might seem a little bit distant, but I do see some connections, some very direct connections in some places, which I will showcase. So I work in human-computer interaction, which I know some of you do, but I also work with the sense of touch, and so the connection between HCI and touch and haptics. Haptics is both your tactile perception, which is in your skin, and your sense of proprioception, which is more in your sense of body forces and movements, and how you know when you pick up an object how heavy it is, whereas the tactile perception would tell you that it's hot or cold or slippery or rough or smooth. I think that people who are immersed in the world of music will know a lot about tactile taction because it's such an integral part of creating sound, but maybe less about proprioception, which is where a lot of my work actually is. And so I call my lab the Spin Lab. It goes back 25 years. When I first started working in this area, I was known for working on very simple devices, literally knobs, things that spin, force feedback devices that spin. And I was trained in an engineering lab at MIT, where the joke was that it was my joke. I don't know if anyone else thought it was very funny, that your self-worth was proportional to the numbers of degrees of freedom in the robot that you build. And so I build knobs, so I was very low on the pecking order. But I had the last laugh, because the reason I was interested in really low degree of freedom devices, simple devices that are very simple mechanically, is because they're simple to build and cheap and inexpensive, and you can put them all around the world and then have the intelligence be in the computation that's behind it, and then what you're trying to do is create images in people's head through their sense of touch. And I thought, if we're limited by the mechanics of building these things, then how about if you keep the mechanics really simple and let software in people's brains do the hard work? And so that's why I think I'm having the last laugh, because my knobs are still going. But I'm going to talk about a little bit a different approach on that, which is where most of my work is now, is affective touch. And so bringing emotional touch, and this is something that I didn't really go into deliberately. It's not where I started. I started on information, communicating information, and when I said that, I was usually thinking of functional information, but I gradually got wrenched more and more and more and more in this direction over the years, because it became increasingly clear to me that what's going on through your sense of touch is so dominated in people's minds by emotion and affect, that they interpret and filter so many things that they feel through emotional lenses, that if you don't take this into account when you're doing interaction design based on touch, you're just going to miss most of the opportunities. And so even for my functional work, like trying to make informative interfaces that like help you navigate or drive or things like that, emotion was starting to come into it, because that was helping people remember and learn things that they use an emotional lens to actually remember and learn. But at some point, we just really jumped in with both feet and started working on emotional robots, because if you're going to do it the whole way. So here's some of the robots in my life. And to start with, the very first one is the upper left. Okay, if Jeremy's in the audience, or a few of the students from the lecture this morning, I'm getting a little bit of repetition here, but I promise this is almost the only repetition. So that was the first robot I ever messed around with. This was in the 80s. It is a teleoperated robot. You can see the working end in front, and then behind the wire mesh screen with a really thick layer of vinyl is Dwight, who's wearing an exoskeleton that is a really honking big robot that's attached to his arm. So when he moves, he can feel the forces that the remote robot is, and normally it would be on the bottom of the ocean pushing a submarine around or something. Okay? And he also has a kill switch hanging from his neck, so that he can turn it off really, really fast. And that's because we had found out recently that that robot could go in a position that his arm isn't supposed to go. We call that a singularity, and it would break his arm. So dangerous. And the screen and the fence there is because the exoskeleton, the working end of it is even more dangerous. Very powerful robot, very strong, very dangerous, and very fragile. It breaks all the time. And I decided I needed to go the other direction, and I told you about the knobs. Okay, so how I can organize some of these things, you might look at some of these and say, is that really a robot? I would consider all of these things robots. I would say complexity is on that dimension, and emotional expressivity and sensitivity is on the horizontal dimension, where more and more we've been moving towards things that are simple and very expressive. And that's where the sweet spot is for me right now. And objects that are too complex, even though they might be very expressive, are not doing what I need them to do. And so that's kind of been this pressure to go in that direction. So, and you'll see a couple of those. I don't have time to go over a lot of them. So I'm guessing this audience mostly knows what affect is, but just to make sure, it's not synonymous with emotion, but there's a lot of connections between affect and emotion. And so, just speaking of emotion, emotion is fundamental to human experience, influencing so many things: cognition, perception, everyday tasks. So it filters, it changes how we our cognitive processes, how we regard things, how we feel about things. Okay, your emotional state when you're perceiving information is going to alter so many aspects of your experience. And so affective computing acknowledges and brings some of that into it, at least my version of affective computing does. Okay, so on that note, let's change gears. And cat video. There's probably better ones out there. I fished around and found this one. This particular cat video shows something that I want you to pay attention to, which is there's a person who is rubbing this cat. I think it's still going. It seems to have stopped. No, he's still moving. They're having a little quiet moment there. So I want you to imagine doing this. Turn on those mirror neurons, okay? Where you're actually feeling the cat rubbing its head. I swear that has stopped moving. And you're feeling the cat, you're feeling it rub. There's a word for this, it's called bunting, when the cat rubs its head against your hand. And picture what you're feeling on your hand and how it makes you feel when you're actually doing this. And this is actually a very interesting exercise, because there's been recent research that shows that the mirror neurons, not mirror neurons, the C-tactile afferents that are in your hairy skin, like the skin on your arm, that when you stroke it and they fire, that's a highway to your affective centers, and you can induce particular feelings of calm and we call it affiliative touch. It changes your emotional standpoint. But what's going on right here is different from that. I actually showed this video at a neuroscience conference where they asked me to give a talk, and I've been hearing all these talks about the C-tactile efferents, and they're all about being stroked. But what I wanted to know is what's going on when I stroke, and I'm using the hair, we call this the non-glabrous skin, the skin that doesn't have hair on it, doesn't have those C-tactile efferents in it, and I'm stroking the cat with that hand, and yet I still have all these wonderful feelings. And so this is one of the mysteries that I'm very curious about. The neuroscientists haven't explained yet to me what is going on here. If any of you actually understand, I'd love to hear it. Oh, there we go. Now, why did I have to click that arrow again? Okay, so soak that up. So here's some more pictures of people and animals. And so there's all this good stuff that happens when you interact with animals. And after a while, Here I was, an engineer building, haptic interfaces. And I was thinking, what's going on with all this stuff? There's all these studies that are coming out, and this was, 15 years ago. All these studies who are saying, like your rate of recovering from a heart attack is much improved if you have a dog. Maybe it's because you go for walks with them, or a cat because you're taking care of them. But there were so many of them that were starting to come, and you're saying, like, how much of it is really literally about the touch? Is that something good is happening when you're doing the touch stuff. And meanwhile, of course, fast forward to the pandemic, we have some recent evidence, more studies that are coming out about what happens to our psyches when we are deprived of the social touch and the small touches that we have as part of our everyday lives because we are in isolation and we don't have that physical contact. And the answer is becoming increasingly clear that social touch, especially affiliative touch, is actually really important, particularly at early in life, late in life, at any vulnerable time in life. Those hugs really count. So here's an inspiration. This is Poppy, who's a golden retriever, very special golden retriever. And so I met her. She was a worker at Canuck Place in Vancouver, which is a palliative care center for children. And so she was a very social dog, very, very rare, very skilled. And so she would go into this Canuck Place. Has anyone ever been to Canuck Place or aware of it at all? So it's a beautiful old mansion in Shaughnessy Heights in Vancouver, very exclusive neighborhood, that was purchased and renovated to be a place where families who are in a town for treatment of different sort need some kind of a respite. And they have all kinds of programming that are for not only the kids who are often in terminal illnesses, but their families. And so there's a lot of emotions around. It's a place where a lot happening in people's hearts and minds. But it's a very calm and beautiful and playful place. There's a lot of happiness there as well. And so what Poppy does is she goes around, she very sadly passed away a few years ago, a year before the pandemic. And she was extremely talented at finding where she was needed and then using her body to kind of intercede, whether it was climbing onto someone's bed and cuddling, or just stopping in the hall and sitting down and kind of leaning against someone and inserting her body into the situation in a way that would just transform the situation. And I started studying, I shadowed Poppy to try and figure out what the heck she was doing. How did she know to do these things? And was there any part of what she was doing that I could somehow pick up on and reproduce in some other way? And sure enough, they have not been able to replace Poppy. And so the director of Canuck Place, who was Poppy's other home, was very interested in seeing if there was something we could do with our robots in some very small way. I do not think we could ever replace Poppy. That's not really my goal, but could we understand it, and could we help a little bit in some of these situations? And so we worked with the caregivers at Canuck Place, not to try and say, can we make a robotic dog that could walk around, but is there something about the way that Poppy did things and the way she used her body? Is there some element of that, some aspect of that somehow could be useful in a different form factor, that somehow, some kind of adjunct to care that the caregivers could find there? And we were getting deep into that. I'll come back to it, but the pandemic definitely got in the way of that. When we could no longer enter Canuck Place, just as we were getting going. So as we talk about sensing emotion from touch, we moved over to this animal model, where by that I mean we studied animals. We're not working directly with animals, but we're taking inspiration from how people work with animals, the benefits that people have from interacting with animals, and seeing if we could model some parts of that and understand affective touch, but also to perhaps confer some of the benefits, okay? Because working with real animals was not going to be practical. I'll just leave it at that. We did think about it. And also we didn't want to work with humans directly, or a human model, because there's so much loading, there's so much social loading involved with that kind of touch. There's so much that could be sexual or uncomfortable or awkward between strangers, where as long as you don't have a problem with animals, which of course is an important segment of people, but there aren't the same kind of social structures of touching an animal that there are of people touching people. And so we thought we could get a lot farther with this. Okay, and so I really give a lot of credit to my former PhD student, Steve Johannen, who was the crazy guy who told me that we should work with cats sometime. So let me tell you a little story about how I think this works. And this is a story I first told quite a while ago, and we're still working on it. This is a long game. So we have Chloe. Let's say Chloe could be a child, could be an adult. It doesn't really matter. And Chloe is looking at a bit. A bit is a small robot. We called them Cuddle Bots, and then we made them smaller, and we made them Cuddle Bits. It was actually New York Times that named them Cuddle Bots. And Chloe, what we want to know, can we actually sense Chloe's emotion through her sense of touch? Sorry, through the way she is touching the bot, okay? If you look at an animal and a person touching the animal, or if you look at a person and a person touching a person, we can pick up a whole lot of information from that touch. If you didn't have any sound, you couldn't see, all you could do is feel someone touching you in an emotionally expressive way, you can get a lot of their emotion out of that. So, can we do that with a machine? Okay, if we could get you to touch the machine the same way you were touching the animal or the person, the information could be there. Can we extract it? Okay, so then cutting edge touch sensing and machine learning is going to be required here. Nothing that was available on the market. You could not go out and buy these sensors. We had to, we're on about our 6th generation of building sensors right now. They're still not quite all there, but they're a lot better than they used to be. But also machine learning is getting a lot better, in case you hadn't noticed. So we're starting to really make some progress there, and I'll tell you about that. And then meanwhile, the bit might say, what emotion is being shown to me right now? So the bit is very small. The bit has to have, sorry, I'm going to adjust this so I can see a little bit, see my own writing here. So the bit has to ask, what emotion is this person actually showing me? So it's not enough for them to actually just sense the gestures. It turns out the gestures are pretty easy to figure out, but what the gestures are saying to them, what they mean, it turns out it's not the gesture, it's the way you're making the gesture that is really important, that has all the tells in it. And so we use those models, we're developing those models, and the bit says, okay, I think that this is what's going on with this person. She's angry. Chloe is angry right now. That's the problem. Okay, now we we have some choices. The bit can have a personality or a therapeutic agenda. The bit can decide how the bit is going to react to this based on the narrative frame that they have placed around themselves. How are they going to treat this situation? Okay, are they trying to just mimic a real animal, or are they trying to do something to help the person? This is all a choice we have when we're designing. But let's say, so the bit has to ask, how do I feel about this touch? Okay, and once they decide, I'm terrified, okay? Then the bit has to physically render with its body terror, all right? So we need a little robot that can render terror in a way that Chloe can actually recognize that, all right? So we need very simple robots. The reason they need to be very simple is because we want to just use them in lots of different places. They have to be really tough. They can't break easily. One of our first environments that we wanted to deploy these in was actually in BC Children's Hospital with kids who were about to go under anesthetic and were terrified. And one of the first criteria that came up is, whatever you do, the kids will throw up on it. So it better be able to handle being thrown up on. It's like, okay. we were thinking in terms of sterilization, but this kind of raised the bar. So they need to be robust. Like, you could throw them against the wall when someone gets really upset, or you could step on it and be strong enough. We figured out how to do that, but the first versions weren't that great. And then, can we actually change Chloe's emotion through touch? So by now, we're saying by the way the bot is rendering its behavior, its physical posture, its movement, can we actually alter how Chloe feels, and can we actually generate a circle here? And one of the reasons this is kind of tricky is because, remember, we're sensing her emotion through the sensors, okay? Through her touch. And then we're actually trying to use the same thing that she's sensing through that same hand to change her emotion. So we're closing a control loop. If we've got any engineers in the room, we're closing a control loop around a system that we're trying to modify directly, which is usually something you try and avoid doing. So this is kind of the system that we're working with. And of course, everything is very noisy. All the signals here are quite noisy. But let me go back a little bit and say, so here's that same control loop. We have, the hand, the robot, we have the expression, the person is making expression, the robot has to recognize something, the robot has an internal emotion, robot expresses recognition, and so we kind of say on the left is the human, on the right is the robot, and you have this loop. One of the advantages of breaking it into the robot, have it be in a robot instead of a real animal, is that we can break this apart and study each of these arrows separately and try and understand them, and that has indeed been how we've approached this. We tried to look at each of these arrows separately, and then once in a while we go back and try and close it up again and say, nope, not quite there yet. And we go back to the drawing board. Okay, so when you put them all together, does something magical happen? So here's the first version. Of course, we had earlier prototypes to figure out to build this one, but this one looks a lot different. It's kind of big and complicated. Has all these things, all these motors in it, and it's kind of the size of a big, heavy cat. Weighs quite a lot. You see a little kid sitting with it, and it's like bigger than the kid. You can see it's a fiberglass shell with what we call force-sensitive resistors, which probably some of you have played around with these. That's what we had in 2005. And then we put a fur jacket on it. And there's several problems with this, which are kind of obvious. One is I called it a turtle with a fur coat on it. It didn't really feel very mammalian because it was this rigid surface. But also, it only could pick up the touch where the sensor was, and there was all this in-between space. It wasn't picking anything up. So these were not ideal. And yet we were able to use this robot to learn quite a bit of stuff. So we looked at how do people interpret its emotion rendering. It could breathe. It could do something with its ears that made them sort of show the, like, I'm alert or aroused, and it could show valence, like which direction, positive or negative valence. So the classic arousal valence quadrant, this object could render quite well in a way that people could generally understand. And we could use it to ask people to say, how would you display different emotions to it as if it was an animal? And then we used video study. We collected the touch data. It wasn't very good. We could get a little bit out of it. And then we could also see how people's emotions would move when the loop is closed. So here's the kind of data. Don't try and read this carefully, but this is what we call a touch dictionary that we got from one of Steve's first studies. And what this is this exhaustive definition of, these are like all the different things we saw people do when they were interacting with it, and we got all kinds of frequency information about how often and for what reason they would use these different gestures just by analyzing video. And we asked them the emotions to express based on this classical two-dimensional model, which, by the way, we don't use this very much anymore most of the time, arousal and valence, and so you sort of make sure we're hitting all the different radial directions on this. And then we get information like this. We're saying there's all these gestures, there's all these frequencies that people were making with them, and right away, you see there's a big problem. It's great if you're trying to find distress because people were quite consistently, they would kind of hold the robot like this when they were distressed. But if you said excited, like, you are not going to be able to get anything from the gestures, right? They would do anything if they were excited. So gestures are not very informative. There was too much confusion on this account. So instead, we would look at the different ways they would make these gestures. And this is something we figured out later on. And so let's just sing the same thing. So the high-level gesture primitives are not enough to discriminate emotion or affective state. We had to do something else. Meanwhile, there's another really exciting result that came about. This is Yasmin Sefagar, and she had the idea of using the same robot we actually, let me just explain, the robot would make these breathing-like movements, and what we wanted to see was there what I call a direct physiological effect. So if you have the robot saying, this was the setup, that's Yasmin, she's holding it just the way it would be, it's in her lap, and the robot is making a breathing motion, and then ran a controlled study, people not particularly stressed out. She wasn't trying to induce any emotions, but she looked at the delta from whatever baseline they were at and saw that just hanging out with the robot doing a breathing motion versus not doing anything else or sitting with a placebo, that substantially significantly would actually decrease all your stress parameters. So just nothing cognitive, just the breathing motion that's actually reacting to you. And if you don't believe me, you should try it sometime. It's like, I call this, it's like taking a pill. This is the taking a pill effect, that you hold this thing and it's moving like this, it just goes, ooh. It's very nice, actually. And so immediately people were saying, oh, I want this. Can you put this in my bed to help me sleep? Or can my toddler do this? It would be great for my autistic child. We'll get back to that. So anyway, I'm taking too long, so I'm going to go on. And we're looking at self-reports, information, as well as physiological sensing, and everything was converging in this way. So the feeling breathing is a visceral cue. And we've leveraged that. We're currently doing a study that's actually exploring, like, can you reproduce it in other form? Can you be doing it, holding it in your hand, if it's leaning against your face, if it's on your torso? Like, do all of these things, how do they affect this direct visceral effect as part of larger things that we're actually trying to do? So let's go into that physical design and authoring behavior part. So if you need to make an object that is expressive emotionally, that people can understand what it's doing, this is beyond the direct physical effect, you need to do some different stuff. The original robot could render static things. It was moving, but it wasn't changing what it was trying to display. And we said, yeah, it can do that, check, it can do that. But it wasn't very natural. It wasn't kind of changing and responding to all these things. And there's lots of things it couldn't do that a real animal could do, which were actually important from a narrative standpoint. When we brought kids in to play with this robot, they would always ask things like, what kind of animal is it? Is it happy? Why is its tail plugged into the wall? And they would ask, when we turn it off in between blocks or something, they'd say, did it die? Because it had a kind of a motor that made noise, and if you unplugged it or turned the power off to let it cool off because it's overheating, then it would stop making the noise. And they really needed answers to all these things. Like, they badly needed answers, and we would always turn it back. What do you think it is? Do you think it died? They got scarred from that one. And so we realized that it was really important to have a story about the bot. And later work, we actually saw that if we controlled the story, then we could control how people regarded it. And so it was actually more important to control the story than to design the movements themselves. Like, you could make it do anything and tell a story and say, that's what it does when it's, like, excited. You know how, like a dog, sometimes it waves its tail and you're not sure if it's waving its tail because it's happy or because it's about to eat you? And so it was kind of like that if you say, oh, well, this dog, the tail waving means this. So that thing of controlling the story turned out to be really important, but we actually needed a different bot to do these kinds of studies. And so we embarked on Creature 2.0. We called it the Cuddlebot. It was very cute when it had a jacket, but it was kind of weird when it was not clothed. I got a large grant, a CFI infrastructure grant, to design this with professional. I thought, wow, we've been doing all this stuff with computer science grad students in the lab, and now I'm going to pay professionals to build a really good one. And it turns out that this did not work well at all, because well, first of all, as an engineer, I should have known better, but they were so game for it that I gave it a chance. That I gave them specifications like it should be happy. I gave them somewhat open-ended specifications for behavior, and then we would have these brainstorming sessions, and we would figure something out. But what we really needed was a lot of iteration. But they thought my $200,000 was only enough for one iteration, and that I was a cheap customer. They did medical technology. So we didn't get to iterate very much. And so we realized after that we actually needed, so we came up with something that was kind of weird and broke a lot. And remember that Sarcos robot that I showed you at the start? There I was, I built one myself. So we needed better physical editing methods, and that started us on a new program, which was this one. There's no sand. This was a work of Paul Bucci. He was a master's student with me at the time. And he came up with this idea of design patterns. So he came up with all the problems we had. We're going to look at one. We're really going to understand the breathing motion. It's so important. And it's very expressive. You think, oh, it's 1 degree of freedom. How much can you do? But you think about real breathing, the way mammals breathe. There's a lot of information. There's the it can go fast, it can slow, but you also can gasp, it can be asymmetric, it can be rattly and rough or smooth and calm. There's so much freedom in how you change the breathing. There's so much information there. But we needed to package it in a way that it was very simple, very strong, and so Paul did this really brilliant thing, which was to turn around, instead of having you have to push the ribs out, he had it so that it sprung with a spring, and then you have the motor, a really cheap motor, just pulls on it and compresses it. And what this means is you can't burn the motors out. If you push on them, you're just pushing on the spring, you're not pushing on the motor. And made it out of these really tough, cheap materials that you could throw against the wall or step on, and it wouldn't actually break it. And came up with these design patterns that you could make them modified really quick and then just cut them out with scissors from a plastic sheet or on a laser cutter for the wood. And then you can see the result is these cute little things that you can put different jackets on them. We have these high school workshops where the kids would make them out of pink or whatever fluffy stuff they have there. And they're very customizable, and you can make all these different sizes and shapes and oblong things. Okay, so here's the design patterns. We ended up with two primary families of them. This one is made out of wood, but we put jackets on it, but you can feel the ribs, and another one is made out of just plastic binder sheets that you cut out literally with scissors and patterns, and you just come up with all these shapes that you can modify and stretch, and they're parametric shapes, and then put these cheap little RC servos in the middle of them, and there you go, and you can make them big or small or whatever. Okay, so how do you program them, though? I said they could be so expressive, but somehow you have to tell it to be that way. And here's where we get to the music part. This was a music person who did this.
Local doodling for effective robot interaction. When describing something abstract like motion, many people may find themselves at a loss for words, and they opt to use non-word vocalizations to express themselves. Doodle translates the properties of your voice into motion on a 1 degree of freedom robot. Doodle detects features of pitch and amplitude and interprets them according to a set of user-definable parameters. With Doodle, users can quickly and naturally sketch effective behaviors in a unique conversational design space.
So this gets to this point of sketching, rapid prototyping, wanted to make quick things, and I could give a whole talk just about this project. But it wasn't a direct mapping from voice to movement. We actually worked with professional sound voice actors with multiple longitudinal sessions to keep modifying the whole system until they had a system that they felt that they could access all the different expressive points and properly use their vocal range to do these different things. And I will tell you that I had the very great pleasure of demonstrating this by myself, with my 10-year-old daughter went along to at a conference in Europe, and the students who ran it weren't there. And I got to see that you could separate the world into two kinds of people, the people who will bark at a robot and the people who will not bark at a robot in front of other people. So that was pretty fun. I wish I had videotaped that demo session. So sensing emotion so there's lots, that was to illustrate a problem. That was one interesting solution to a problem, but this whole problem of giving expressive movement to a robot body remains a very challenging one that we've been working on in a lot of different forms. I just don't have time to talk about those, but it's one of the ongoing challenges is how do you actually program and author behaviors for them. Okay, so if we're actually now sensing emotion from touch, and need to pick the pace up here a little bit. So we have three big problems which define the current work that we are doing in this. Now I'm into emotion modeling, not gesture, but emotion. And say, first of all, we need better touch sensors. I showed you those FSRs, the force-sensitive resistors on the fiberglass shell. Not good enough. We need better ones. We're working on that. I'll talk a tiny bit, but not the most recent stuff is being a drama queen right now. It's not falling into place very well. Accepted psychology models of emotion assume static and single-valued emotion states. They say, that two-dimensional model of valence and arousal, it's so common, it's so pervasive, it's a psychologically founded model, and it's not wrong, right? We can all make sense of it and place our emotions on that thing. But when you think about your lived experience, you think about emotion and you say, it's not single-valued. You can totally feel different emotions at the same time, and it doesn't stand still. They're moving all the time, and these static snapshots, they don't make sense. And so when we're trying to build applications where you're estimating people's emotion in real time, and then adapting an interaction response to that. Our default, our very first assumption is that the emotion is a moving target. It is not standing still. And this is real. It's how people are. Think about it. Okay, so this model of valence and arousal does not work for those two reasons. And so we looked for alternative metaphors to model this. It's an inadequate representation of emotion, and when we're trying to build it into real-time computational models, it doesn't work. So, so that was a big challenge. And then we have this other problem is we're trying to do this work in the lab, and we need to be working with the real thing. With real, we call it authentic emotion, not. I told you about, we did that touch dictionary by asking people to say, express this emotion to the robot. That's simulated emotion. People were pretending. We actually don't know if it's the same, if you do the same thing as you would if you were really feeling that emotion. We need the real thing. And so we needed to come up with some, and this is a chronic hard problem in lab studies for emotion work, but we needed to come up with some protocol that would actually allow us to deal with all these different things. Okay, so back to the sensors. I'll just show you one. This is getting a little bit dated, but it's still the best video that I have. So I'll show it to you. We're trying to do much different things now. So that was work of Anna Flagg. Actually, I want to go back for a second and not give it away. She responded to a challenge. I said, the holy grail is we need a fur sensor that can actually detect these really light touches in the fur. Remember, we had the turtle in a fur coat, so this was like really reaching at that time. And around then, we actually saw something. I was wondering if anyone actually could guess what was going on with that thing. So basically, she did this as a live demo at a conference with a camera on the screen. You could blow on it, and it would be so sensitive, it would catch the blows, the whisper of air, or if you could, just fluff the fur, it could tell those apart. Anyone guess what was going on there? Can't see. Could anyone guess how this works? Temperature? Nope, not temperature. Air pressure? No. You're getting warm. Movement of the fur, yeah? Some of those hairs are like part of the sensor, right? Very good. Bullseye. Yeah. It's resistive. It's not capacitive, it's resistive. And so we were inspired by this work by Leah Buckley at MIT back then, and she did this thing on Thingiverse, which we just took their idea and really ran with it, and it's one of those things where the devils are in the details. These are conductive threads. This was my first time ever using machine learning. It was quite a while ago. Okay, and if you squiggle these conductive threads together, and you have these ground planes, and then you look at the stochastic frequency with which they interact with each other, so it's a stochastic function, you can actually do machine learning on the resistance that's coming across these squished together things and detect gestures from it. Now, she just showed that you could, what the original work just showed that you could get something to happen, and then we threw machine learning at it, but also found that getting it to work, get the exact right density of furs and the lengths of the threads and all these things, and then get the right training algorithm on it. And then when you did that, you could actually get this very high performance. We did this study where you had actually was a capacitive sensor by having these two conductive layers of striped fabric. So we had that to get the deep touches and the fur on top. And when we put these things together, we found that, wow, you could really tell the gestures apart. Remember, don't get too excited, it's just gestures, but still, it worked really well for gestures. And one of the exciting things was that you could also tell people apart. So people made the gestures in a very recognizable way, but they made it just different enough that we could actually identify who the person was. And that was the big surprise there. It was like, wow, you mean we can have the little class pet and they know it's Johnny and not Jane who's petting it right now? Because people are that distinctive, and that was where we started to say, oh, there really is a lot more information in here. But we want real emotion. So that was about sensors. And by the way, what we're doing now that it's being very elusive, I'm working with a materials scientist to make these polymer gel things that can do shear and all these very skin-like things that we can just make in custom sheets and drape them over everything. But there's a little, they keep not quite working right yet. If we want to access real emotions, this is this crazy project that was started by Laura Kang a long time, where we started developing this protocol, and so this is mostly about protocol, asking people to tell an emotional story of something that happened to them, a memory, so reliving a memory while they're touching the robot, and use that to elicit the gesture. And the first time we did this, we actually had to pull the experiment. We had to close it soon because it worked way too well. That the people were getting so upset that we felt like we were exceeding kind of what we ought to be doing in our ethics application. We did not have counseling there afterwards. And so we put people in private in a closed room, and they called us when they came out, and we were studying the gestures they were making. We found out that we didn't have good enough sensors at this point, so we came back and we have polished this setup even more so to actually, Laura Kang is still working on this and coming back and developing more powerful models using more advanced sensors that we actually have right now and collecting the data in different ways, but still elaborating on this protocol for doing this. And one of the amazing things, the very first pass on this protocol, we initially started just saying, let's just see if we want to use EEG as kind of the gold standard for detecting emotion. And so we thought we would just try and duplicate some results that we found in the literature, which we did using EEG, but we had them play a game using a keyboard to use the left and right arrows to control the stressful game. And we, just for yucks, we put a force sensor underneath the keyboard to get the energy with which people were tapping on the keys. And that was the haptic input, was that we call it key press force, how they were tapping the left and right arrow keys while they're playing this game. And we compared that with brain activity, which has been well studied. It's pretty intrusive. You're wearing this hairnet, right? Okay, and this is inside, it's a kind of a slightly stressful, scary game. We use that for an emotional elicitation task because everyone played the same game and they sort of had to go through the same steps of the game, and we kind of knew where the scary parts were. But what we would actually do was take them through this protocol where they played the game and we had them all rigged up with sensors and they were using the keyboard to control the game. And then we took them through multiple self-report passes afterwards where they're watching video of their own game play. And first they would so they first played the scary video game, wearing all this stuff, and then they'd annotate it with calibrated words. In other words, they told us what these words actually meant to them personally, because not everyone is the same. And then they'd watch it again, this time with a continuous joystick telling us what their emotion was at that actual time, so we had this continuous trace. So we have all these different layers. We call it a multi-stage, multi-step emotion elicitation protocol. And this is the kind of data we actually got out of it. So affective modalities would be on top is the EEG. Down below you have the key press force, which was originally not the focus of this whole study. It was just there, because we could. And then there's a joystick that we used to actually do the emotion trace, which they labeled with their calibrated words and said, this is what I mean by this position of the joystick. Okay, and so what came out of this was pretty cool, because when we ran machine learning on this in different ways, this is what the brain activity, I don't want to get too much into the data, but just say right is good. Right is more accurate, left is less accurate. And so the brain things, the EEG models that were running on EEG features also only were not doing so great. This was using machine learning. And the key press force, which remember, this was a throwaway, we didn't expect this to do anything, was outperforming the state-of-the-art EEG. Okay, so that's pretty cool. And then, so that's playing a video game, key press force outperforms EEG. But now, our most recent data, we're doing it on actually stroking a furry robot while reliving an emotional story. If you remember that early protocol, that data works even better. And so got a discussion with Jeremy about why this might be. It's not necessarily true that the data isn't in the EEG, but EEG, there's a lot going on. Whereas in the touch data, it's easier to find, it's a simpler signal, it's more direct, and we're able to see it in there. So non-invasive, they don't have to wear anything, you can put it in all kinds of objects and just pick it up and pick this emotion up. So now we're trying to build on that. So quickly, I just had to throw this in, it's our very latest work. We're working on emotion modeling. So there's emotion regulation is when you try to regulate your own emotions. We do it all the time. There's people who will say, psychologists who say, all emotion is regulated. We're not capable of having emotion that's not regulated. I'm still pondering about that one. But these are different places or points that you can regulate your emotions. The situation, attention, appraisal, response. This is for 20, 30 years been accepted. James Gross, work from Stanford that talks about this. What we mean by those, this could be the person experiencing the unpleasant situation. Attention is that where your attention is going. Are you paying attention to this thing? The appraisal would be the cognitive part. How are you feeling, how are you viewing this situation? Are you viewing as a positive thing or a bad thing, for example? And your response might be physiological, how I feel, what I'm doing, what's actually happening with my body. All of these things are opportunities for regulation, and people regulate at all these points. For example, you might change the situation, get yourself out of there, make sure this never happens, you're never putting yourself in this stressful situation. You can redirect your attention, you can change how you think about something, we call that cognitive reappraisal, or you can try and directly change your response. Now we say, how can touch help with any of these phases? We're trying to move our affective robot work onto a more psychology-founded basis. We say, according to these theories, where should we intervene? What's going on? So that earlier work where I showed you, the direct physiological effect, I'm taking a pill, that's where that's working, okay? It's the direct physical, you have an upset reaction, this changes through this direct effect. That's stage one. You require the stimulus to be present, you can't really learn it, it's just going to be this automatic thing, I have to take the pill, okay? But it could work on a cognitive effect too. It could lower your emotional intensity so that you can actually calm down enough that you can start to say, okay, I got to get a hold of myself. I don't know if you've ever seen someone having a panic attack or if you have a tendency to have them yourself. I have a family member who does, and this is a very real thing. If you're so upset you just can't get a grip, you need something to sort of calm you down enough so that you can start to bring cognition to play. So that's an important enabler. Okay, it can also provide a path to access your cognitive resources, so I can actually say, all right, I'm bringing my mind into it, and I might have all kinds of knowledge. For example, I say, okay, this is something I can do to calm myself down, this is some thoughts I can have, I can put myself in a different situation, I can remind myself that this is not that important. All of these things that I have knowledge about, now I can start to do those, and the touch can be a cue to actually help you do that. And then if the robot is actuated, it can distract your attention, and it can help break you out of a rumination. For example, if the dog comes up and starts pushing your hand and maybe takes your mind off the thing, that would be an equivalent place. And so we were considering, look, there's all these other ways that our little haptic robot or a haptic object of some sort could actually intervene and start to be involved with this. And so what my student Preeti Vyas is actually working on right now is trying to insert these little robots into, this is just one of the scenarios where she's trying to work with cognitive reappraisal and picture and then start to run studies that go specifically after these different psychologically founded pathways. And they're so simple that we can send them home. And this is just showing we've got the kind of the setup where we're trying to build these to do these in-home longitudinal studies. Okay, and where I wanted to close up was just to say a little bit about haptic robots in care contexts. I told you a little bit, we're trying to figure out how to actually make them work in psychologically grounded emotion regulation context, but we've been working on this for quite a while. And when we're actually working in these areas, you can't just drop in and say, hey, we got a robot, let's put it to work. We have to spend a lot of time in the place, understanding how they are working, what they need, what their strengths are, where it's not working so well. And so, and this is a long game, and we were actually deep into two of these places when the pandemic hit, and those two PhD students were hit pretty hard by this. But one of them was Connect Place, which I've told you about. trying to work with the caregivers there who are working with kids with all different kinds of situations and looking at the different things they had and how we could actually kind of incorporate haptic objects as adjuncts into the care that they were doing. Another place was a dementia center. I'm sure you have this in Montreal as well. So this would be a provincial center where kind of some of the most difficult cases that were not doing well at home would come in and spend 2 or 3 months here trying to figure out how to work with these patients in a way so that they could be stabilized and sent home again. And a lot of times these patients would be very distressed, sometimes violent, very hard to reach in many cases. And so what these caregivers were looking for, and they asked us to come in, was to find ways to use a robot-like object that was designed to their specification to be, again, this adjunct. So, for example, not to replace a caregiver, but the caregiver could use it in a kind of a triangle to have conversations and engage a distressed individual in some kind of care. And then finally, one project that did go to completion, but it took a very long time, was in the preemie ward at BC Children's, with a collaborator there who, this is Lisa Holsty, she's an occupational therapist, who works with neonates and in particular was an expert in infant pain and had demonstrated that necessary medical events, they call them, like needle sticks, for example, would actually register as pain to the premature baby who is already going through an awful lot and cause early brain damage. And so it turns out that if you reduce the experience of pain that they're feeling, you can reduce the brain effects. And so this became a very critical thing to do. And so Lisa saw our robots and said, what we need to do is turn your robot inside out. I don't want a fuzzy robot that the infant can hold, because it can't, but it could reproduce what the standard of care there was actually kangaroo care, was the mother holds the baby on their chest. And the mother's breathing was thought to be very instrumental in actually lowering the infant's pain response, their perceived response to the pain, which is very important. It's what we were looking for here. And so she wanted to build a flat platform version of the haptic creature that the baby could run. This was our first version, and then a later version that's more professional. These went through actual clinical trials in BC Children's. It took forever. It took 10 years. We had to raise funding. The BC Children's actually swapped out all their incubators halfway through the study, and we had to ditch our prototype and start from scratch because it didn't fit anymore. And the X-ray, don't get me started on the X-ray thing. But eventually, it got patented, and now it's being licensed to a major incubator manufacturer because the clinical trials actually showed that it does have this pain protective event. But what I wanted to tell, one of the most interesting parts of the story, at least to me, was that that's the design for the baby. But the baby is not the only one in this story. There's also the parent. Okay, and the nurses. And so the bonding between the baby and the mother is one of the most important things happening right there, and it's very injured or very much at risk due to the whole premature birth situation where the mother is separated from the baby before they're ready, and then she can't touch the baby for a long time because it's in the incubator. It's very scary, and they're not able to bond, and there's often very bad outcomes from this situation, this prolonged situation. So anything that could damage the mother-baby bond is just not okay. And so my colleague, who had worked with the nurses and the parents for many years, knew that this was a problem. She says, you can't go in there and use a robot to replace the mom. That will just not be allowed. It doesn't care how good it is for the baby. The damage it will do is more than the benefit it would confer. You can't do that. And so that was a design principle. We designed this thing to not be a robot. It's an appliance. It is an appliance. I called it a robot earlier, but it is an appliance. Okay? And what it does is, in a way, it's a telerobot. We actually recorded the mother's heart rate and breathing respiration rate and programmed it into the incubator, which basically does the insert, which it's just a platform that goes up and down and has a heartbeat, and it's warm. Okay, that's what it does. It's not very complicated, but recorded the mother's parameters, and so when we did all the trials, this is the data that actually ran it. The babies had their own personal settings, which was their mom's information. Okay, and that changed everything. The mother. Now, when we interviewed the moms, they said things like, real quote, "It's a backup of me. It's there when I can't be there. It's taking care of my baby when I'm not allowed to. It makes me feel better about it." So it didn't replace the mom, it extended the mom. And so this was really critical to its being accepted in this environment. We could not have done the trial if we didn't have that acceptance. And to strengthen the bond instead of putting it at risk. And I am going to stop there. I think I went a little bit over. And if there's time for any questions, I would love to hear them. Thank you.